Unsteady flow and heat transfer of viscous immiscible fluids between two parallel plates. Abstract: this paper studies the unsteady flow and heat transfer of two viscous immiscible fluids between two parallel plates. The partial differential equations governing the flow and heat transfer are solved analytically using two-term harmonic and non-harmonic functions in both fluid regions of the channel. Effects of physical parameters such as height ratio, viscosity ratio, conductivity ratio, Prandtl number, Eckert number, periodic frequency parameter and pressure on the velocity and temperature distributions are given and illustrated graphically. Keywords: unsteady flow, heat transfer, immiscible fluids, oscillatory pressure gradient. Nomenclature. Introduction. Problems involving immiscible multiphase flow and heat transfer and multi-component mass transfer arise in a number of scientific and engineering disciplines. Important applications include petroleum industry, geophysics, and plasma physics. In modeling such problems, the presence of a second immiscible fluid phase adds a number of complexities as to the nature of interacting transport phenomena and interface conditions between the phases. In general, multiphase flows are driven by gravitational and viscous forces. There has been some theoretical and experimental work on stratified laminar flow of two immiscible fluids in a horizontal pipe 1,2. 3 studied two-phase MHD flow and heat transfer in a parallel plate channel, with one of the fluids being electrically conducting. Two-phase MHD flow and heat transfer in an inclined channel was investigated by 4. Later on, convective magnetohydrodynamic two-fluid flow and convective flow and heat transfer in composite porous medium was analyzed by 5,6. Fully developed flow and heat transfer in horizontal channel consisting of an electrically conducting fluid layer sandwiched between two fluids layers is studied analytically by 7. All the above studies pertain to steady flow. 8 to 11 have presented analytical solutions for unsteady/oscillatory two-fluid and three-fluid flow and heat transfer in a horizontal channel. However, most problems of practical interest is unsteady. Keeping in view the wide area of practical importance of unsteady multi-fluid flows as mentioned above, it is the objective of the present study to investigate unsteady flow and heat transfer of two-fluid model in a horizontal channel. 2. Mathematical formulation. Consider a two-dimensional unsteady flow of two immiscible fluids in a horizontal parallel permeable plates, extending in the z and x direction. The region I, is filled with a viscous fluid having density, dynamic viscosity, specific heat at constant pressure thermal conductivity, and the region II, is filled with a different viscous fluid having density, dynamic viscosity, specific heat at constant pressure and thermal conductivity. The flow of both regions is assumed to be fully developed and fluid properties are constant and driven by a common pressure gradient in region I and by pressure gradient in region II. The two plates are maintained at constant temperatures. Under these assumptions and taking and the governing equations of motion and energy, Loharsby and Sahai, 1988, are given by where U is the x component of fluid velocity, V is the y component of fluid velocity and T is the fluid temperature. The subscripts 1 and 2 correspond to region I and region II, respectively. The boundary conditions on velocity are the no-slip boundary conditions which required that the x component of velocity must vanish at the wall. The boundary conditions on temperature are isothermal conditions. We also assume the continuity of velocity, shear stress, temperature, and heat flux at the interface between the two fluid layers at y=0. The hydrodynamic boundary and interface conditions for the two fluids can then be written as 5. The thermal boundary and interface conditions on temperature for both fluids are given by 6. By use of the following non-dimensional quantities. 7. And for simplicity dropping the asterisks, equations 1, 2, 6 becomes region I 8, 9, region II 10, 11. Where is the ratio of viscosities and is the ratio of thermal conductivities? The hydrodynamic and thermal boundary and interface conditions for both fluids in non-dimensional form become 12, 13. 3 solutions. The governing equations, 8, 2, 11, are solved subject to the boundary and interface conditions, 12, and 13, for the velocity and temperature distributions in both regions. These equations are partial differential equations that cannot be solved in closed form. However, it can be reduced to ordinary differential equations by assuming 14, 15, 16, where J1, 2 for region I and region 2 respectively. By substitution of equation 14, 2, 16, into equations 8, 2, 13, one obtains the following pairs of equations. Equations 17, 2, 25, along with boundary and interface conditions 26, 2, 29, represent a system of ordinary differential equations and conditions that can be solved in closed form. Since the solutions can be obtained directly, the expressions are not presented. The results are depicted graphically and are discussed in the next section. For results and discussion. In this section, representative flow results for oscillatory flow and heat transfer of two immiscible fluids between two parallel plates are presented and discussed for various parametric conditions. The flow governing equations cannot be solved exactly. However, the closed-form solutions were found considering the cosine function for frequency parameter on velocity and pressure is assumed. The solutions are depicted graphically in Figs 1 to 7 for different values of viscosity ratio, periodic frequency parameter and pressure on the flow and thermal conductivity ratio, Prandtl number, and Eckert number on temperature field. The parameters are fixed as 1 except the varying 1, PR equals 0.7, EC equals 0.5 and equals 450. T. Figure 1 shows that velocity profiles are suppressed for large values of viscosity ratios. The flow profile is large in region 2 compared to region I, and the similar effect observed for different values of viscosity ratio on temperature profile as shown in Fig 2. Figure 3 and 4 observed that the variation of periodic frequency parameter on velocity and temperature profiles respectively, as increases the flow increases, the increases temperature profiles is also increases in both the regions, since the solutions are approximated by function of exponential function of. Keeping in view the physical model of the flow of two immiscible fluids such as water and oil in petroleum industries, a study is made to know the effect of pressure on the flow as shown Fig. 5. We have considered different values of pressure for two fluids separately. For positive values of pressure on upper and lower fluids, the flow is promoting. For positive values of pressure in the lower region and negative values of pressure in the upper region display the effect of maximum velocity in region I. On the other hand, if we take negative values of pressure in lower region and positive values of pressure in the upper region also show the maximum velocity in region I itself, but the flow direction is opposite. Assigning negative values of pressure also show the similar effect to that for positive values of pressure except in opposite direction. It is observed that controlling the pressure parameter one can also control the direction of flow, which has immense applications in flow reversal problems. The effect of thermal conductivity ratio is depicted in Fig. 6. As the ratio increases, the magnitude of suppression is large in region I compared to region 2. This is obvious because the upper plate is maintained at a low temperature compared to region I. Figures 7 and 8 display the effect of Prandtl number and Eckert number respectively on temperature field. It is seen that temperature increases with increase in Prandtl number as well as Eckert number. Since the values of Prandtl number are very small for liquid and metals and it is very high for highly viscous fluid. Thus one can conclude that the flow can be controlled by considering different fluids having different viscosities, periodic frequency, and applying different pressures.